All right, let's get started. I'd like to begin by acknowledging we're meeting on the lands of the Worimi and Awabakal people, and in particular, I believe, of the Pambalong clan, and acknowledging their leaders, past, present, and emerging. And it's also my pleasure to introduce tonight Hannah Schunker, who's going to speak to us about the sun. Hannah worked as a research scientist at the Max Planck Institute in Göttingen for, I think, about 14 years before coming to join us in Newcastle in 2020. And in 2023, she was awarded a future fellowship by the Australian Research Council, which is supporting her for... Well done, Hannah. And that's supporting her for her research for 4 years, after which she will revert to the normal position at Newcastle. So anyway, thank you, Hannah, and please.
Thank you for the introduction, George. And thank you all for coming. I'm impressed with the turnout. I'm going to speak to you today about our magnetic sun. So what you're looking at here are observations of the outer atmosphere of the sun, which we call the corona. See here is guided by the sun's magnetic field. Where it's brighter, the magnetic field is stronger. Where it's darker, it's weaker. So I've just zoomed out here. You can see that the entire sun is covered with magnetic field. It's on small scales to global scales. And these regions you can see that are brighter are what we call active regions. So active means that the magnetic field is changing. It's active. And this is where the magnetic field is stronger. You can see the beautiful loop structures that reach out into the atmosphere. You can see them a little clearer at the solar limb there. And you can see that they're changing on timescales of minutes to hours to days to decades. So if you look at this active region here, this is a large active region. I've chosen it specifically because it's very easy to see. And it has some very bright solar flares. If you see a sudden brightening here, it'll come. There we go. That's what we call a solar flare. So what's happening is the magnetic field, the loops, are changing very rapidly. They touch and they release energy into the atmosphere of the sun. So this is happening in the corona. We've taken a step back and we're taking observations now from further away. What you can see is the density of particles in interplanetary space. So here it's more dense than over here. That circle at the center that you can see, we have blocked out the light from the sun because if we're looking at all the light from the sun, it's too bright. We can't see what's happening in the background. The white circle indicates the size of the sun, like what we were looking at in the previous observation. So the sun's there and we're looking further away. You can kind of already see the structure is pointing all away from the sun. And this is what we call the solar wind. So I'm going to play the movie. And you'll see these ejections that happen out into interplanetary space, out into the solar wind. So sometimes, not all the time, a flare is associated with one of these coronal mass ejections, or CMEs. They're not always associated with each other. So this is a particularly large one that I've chosen, and you can see it. There was a small one, and then the large one comes. There we go. So that's almost half the sun. That's quite large. So this is ejecting charged particles and changing the magnetic field of the solar wind. So the solar wind consists of magnetic field streaming out and charged particles. So these changes in the solar wind are what we call space weather. There's a few different definitions of space weather. But essentially, it's changes to to the structure of the ambient solar wind. And the solar wind extends out until all through the solar system. What we are mostly concerned with is how space weather affects us here on Earth. But if you're an astronaut or you're living on Mars in the future, you also care how the space weather is on those planets. Most of the observations we have of the sun are from the Earth's perspective, because it's the easiest thing we can do is put a telescope out there in space and observe from the Earth's perspective. But we did have a mission called Stereo, where we sent 2 satellites out around the sun and observed the sun from 2 directions, so in stereo. These observations are from one of those satellites looking side on. So here you have the sun, it's blue, ignore that. Then we have the solar corona out here, which were the observations you were looking at before, where we see these CMEs. We have the planets orbiting. This is Venus, and this is Earth, not to scale. What you are observing here again is the density of particles in the solar wind. So these observations, I think, show very nicely and very beautifully the effects of the solar wind and how the sun affects what is happening towards the planets. So you'll see a CME occur here, if you keep an eye on it. There we go. You see the particles ejected into the solar wind. When they pass by Venus, they'll interact with Venus's atmosphere. They travel onto Earth, and you can see them interacting with the space around the Earth here. These observations are quite unique. This observation is quite special. We only have a few of these, but it shows it very clearly. When this perturbation to the solar wind interacts with Earth, it can change the magnetic field. And this is what we call on Earth a geomagnetic storm. So it changes the structure of the magnetic field here. So the Earth's magnetic field, there's the Earth, can be represented like a bar magnet. We have the North Pole, we have the South Pole. And these lines represent the magnetic field joining the 2 poles. So we have that general global structure. From the right, this is a simulation. I should say this is not an observation. We are simulating the effects of a strong CME coming from the sun and interacting with the magnetic field. The colors here show the density of the particles. So this is sort of the ambient state. And you can see that the density of the particles here is larger because our magnetic field protects us from all this radiation. So it's pushed around the edges of what we call the bow shock and around the Earth. So we owe a lot to our magnetic field for protecting us from this radiation. So the CME comes in, and what you will see is that the magnetic field here, which is initially quite large, contracts. So it contracts right down closer to the Earth. You'll also see that the density of the particles increases, of course, because we're having that come in from the CME, from the sun. And this gets quite close to the Earth. So it changes the Earth's magnetic field. Coronal mass ejection. That big fluffy thing you saw the sun push out into the solar wind. So why you care about all of this are the effects of space weather. There are a number of effects. One, I think that's very clear, is the radiation. For life, it's important. If we suffer from radiation, our cells are damaged, and if these replicate, then we have cancers, and this is not good for life. So life as we know it. In addition, with the change of the magnetic field, so there's a little bit of physics, when the magnetic field is changing rapidly, this can generate a current. And it will generate a current in anything that can carry a current. And we as humans have designed some very efficient current carriers. So we have long distance power lines that traverse through countries over the Earth, and it can generate current there. So I'm going to talk about a few specific examples of the effects of space weather. One of them is the 1989 Quebec power failure. Here we are looking at a space observation of North America. This is the East Coast. This is Florida down here. All these lights are New York. And what you can see very clearly is the border to Canada, which is dark. So there was a CME, there was a geomagnetic storm. It caused a current to run through the long-distance power lines. When it arrived at the power station, the current was so strong that it heated up the metal and essentially burnt the transformer. So that's what you're looking at here, which took out the power. And just to be clear about this, these transformers, which you just saw, sit in containers of this size. And here is another image of the transformer. You can see the human hands there just for scale. So you can't go and just pick up one of these transformers off the shelf and replace it. You need some kind of mitigation strategy to bypass this transformer and try and get your current running again through the other transformers in the power station. So that left 6 million people without power at night in Canada in winter for 9 hours. So that's one of the most extreme examples. A more recent example, so this is from 2022, was a satellite deorbit from the Starlink satellites that were launched by SpaceX. So I think most people are familiar with the Starlink satellites. 60 of them were launched, and only 20 of them made it to orbit. Now, this is due to the charged particles entering the atmosphere. Here we are looking at, well, the ground and the layers of the atmosphere above. Here we have the ISS. And if you're trying to get satellites up to this height, you need to calculate very well the density of the atmosphere that you need to get the satellites through up to that height. But if the density of the atmosphere changes, you may not make it. You won't reach orbit, and you will deorbit or crash. But deorbit's what they're calling it. So the density, it changes the density of the atmosphere. And this was only a loss of $30 million to Elon, which probably doesn't, mean much to him. But it can be important. The last one I want to mention, because it's also important for defense purposes, and this one might be again, important. The Cuban Missile Crisis in the 60s, I think it was in 1969, there was a solar storm, and there was a missile placed in Cuba pointed at the US. So tensions were high. The US had a ballistic missile early warning system, which would ideally tell them if there was an incoming missile and to, things have changed, and to stand to attention. But there was a radar disruption, and they interpreted this as intentional jamming of the radar by the Soviets. So they wouldn't be able to detect if there was an incoming missile. And so this escalated things. But what had happened is that there was a solar storm, a geomagnetic storm. The charged particles had entered down into the atmosphere and had increased the width of the layers in the atmosphere. So in particular, the ionosphere. So just let me zoom in on this part at the bottom. Might give you a better idea here. So with communications, over the horizon communications, we can't send a signal through the Earth. So what we do is we bounce it off the upper atmosphere. We send a signal up, it bounces off the atmosphere and arrives where you want it to be received. So you have to know the angle that you need to point it at to arrive at the correct location. But if that width then changes, if it lowers, your signal will not reach the receiving station. And so this is what had happened. It didn't escalate to anything because someone had notified that there is a radio blackout. It's likely a geomagnetic storm. But it does have implications for communications and also for GPS, which is something maybe more relevant today and in everyday use. So GPS has an accuracy on the order of meters. But if there is a change in the density of the atmosphere and the signals are not reaching where they should, or they're reaching with a delayed time, the uncertainties increase to sort of tens to hundreds of meters. So that's important more for defense than Google Maps. That was the last practical one. But the last most beautiful one I would like to talk about, and I guess the most famous, is the aurora. So we have a cartoon here. CME comes in, it changes the magnetic field, allows the electrons and ions, the charged particles, down into the atmosphere. So they're guided by the magnetic field. And at the poles is where the magnetic field reaches down into our atmosphere. And so what we have there are these auroral ovals. So here we have an image of the aurora in Alaska. So this is at 65 degrees north. So it's quite close to the poles and somewhere where you would expect to see an aurora. You've got the magnetic field coming down to the poles there. And this was taken in May 2024, so just last year. Beautiful, stunning pictures. If for nothing else, it was worth coming for these. But even in Melbourne, at 38 degrees from the equator, we could see the aurora. So this is looking south. This is in New South Wales, similar latitude, beautiful reds and oranges. Went in the wrong direction. Perth, a little closer to the equator, could also see the aurora there looking south. Even in Queensland, so this is only 30 degrees or 29 degrees from the equator. So this aurora, which is usually restricted to the poles, has extended very close. And this is what it looked like in Newcastle at that time too. I was livid, and just to rub salt into the wound, this is what the aurora looked like in a small town in Germany where I used to live, which is typically covered in a thick blanket of grey clouds. So even it was visible there. So that's sort of the explanation of what space weather is, how it affects us and why we should care. But space weather is driven entirely by the sun's magnetic field. So to understand space weather and perhaps be able to forecast it, will there be a geomagnetic storm? Will it be strong? When is it going to arrive? We need to understand the sun's magnetic activity. At the moment, we're limited to basically nowcasting. We have satellites that can tell us what the charge and the magnetic field is with about an hour's notice before it interacts with the Earth. But this is not enough time to reschedule your spacewalk on the ISS or alert people that communications are about to go down when your submarine is at the base of the ocean. So it can take anywhere between 18 hours to 3 days, depending on how much energy is in one of these CMEs, to reach us from the sun. Even if you see a large CME, it may not be directed exactly towards us. It may go above. It may be deflected to the side. We don't have a very good idea of how they propagate from the sun to the Earth. So we need forecasts. So what do we know about the sun's magnetic field? Here you are looking at the observations of the outer corona of the sun, as you've already seen, from 1996 around to 2020. What do you notice? There's pattern, it's getting darker, it's cyclic. So it's darker, it gets brighter, it gets darker, it's brighter. And this may have given you a clue. This is what we call the solar cycle. So the magnetic field amplitude and the activity increases and decreases. It has an 11-year period, I'll tell you that so you don't have to count. So we have these active regions. We can see this in the outer atmosphere, the outer corona of the sun, and this is what affects space weather directly. We know that those loops are associated with what we call sunspots at the surface of the sun. So here you're looking at the light, the white light coming directly from the surface of the sun. So this is like if you had a thick pair of sunglasses and you looked at the sun. And please don't do that without the appropriate eyewear. But this is what you would see. And these are the most straightforward observations to make. So we've had observations like this of the sun since Galileo first pointed his telescope at the sun, which was 400 years ago. So for 400 years, humans have been counting the number of sunspots on the surface of the sun. And it's a direct measurement of how much magnetic activity there is. So this movie gives you an idea of how the sunspots change, how many there can typically be on the surface of the sun. This is at a particularly active time. This is the same time as we saw the flares last year. So you see quite a few spots, but you get an idea of how big they are, how small they are, where they appear. So by counting these sunspots, we have a very, well, it's relative, but we have a long record of the solar cycle. So here we have sunspot number since 1700 up until today. So you see that that 11-year period is very regular. The amplitude changes, or the number of sunspots changes, but that 11 years is very regular. Now, we've only had space-based observations, just to give you a little perspective, since 1996. That's when we could make observations like this. We can't make them from the ground. So that's here. So we've got almost 3 solar cycles. And here we are today. And I put solar maximum with a question mark, because we don't know we're at the maximum till we're on the other side. So we're in the solar maximum phase. The sun is very active. This is a still of the movie, and you see here this flare, and this is the flare that generated the CME, that generated those beautiful aurorae we saw, so from May last year. So this is a strong flare. We know that that magnetic field is connected to the sunspots on the surface. Now this is a particularly complex active region, had a lot of energy in it. And we know that these sunspots are associated, so keep an eye on this one and this one. Strong concentrations of magnetic field. So you see that this is a sunspot here, and this has many sunspots in this active region. These observations are of the magnetic field directly. This is the only place we can make observations of the magnetic field itself. Black indicates magnetic field going into the sun, and white indicates magnetic field coming out. So I'm just calling them plus and minus. You can call them north and south if you like, but this is a little more complex than what we have on the Earth, where we just have the bar magnet. So we use plus and minus. Again, you see the entire sun is covered with magnetic field, but the active regions really are the feature that dominates. Now we see the movie, and you can see how the magnetic field evolves. So watch this one here. You can see it appear on the surface. There's one up here that forms somewhere. There's 2 there that formed. So we can see that the magnetic field comes from the interior of the sun somewhere. Somewhere below the surface, it's coming up and pushing through the surface and creating these loops in the outer atmosphere. So to be able to forecast this, we need to understand how active regions emerge and where the magnetic field is coming from. So we need to see inside the sun. We know something about stellar structure and the sun just from classical observables. We can observe the chemical composition, we know the temperature of the sun, we can look at the orbit of the planets, we know the mass. So in the core, we have the fusion of hydrogen to helium. And that's the definition of a star. It's a fusion reactor. Then heat and light is radiated away. So it's just like stepping away from a campfire. Heat is radiated away. In the outer level, we have the convection zone. Here, The plasma is heated from below, it's cool on top, so it sets up convection cells. So we have plasma in convection cells in the outer layers. And if we zoom in at the surface, we have observational evidence of that as well. This is an observation from a ground-based telescope. This is state-of-the-art, the highest resolution observations of the surface of the sun that we have, because we can't get an enormous mirror up into space. So what you see here is what observers first called, without knowing what it was, granulation, because they look like little granules. That was it, granulation. But these are the tops of convective cells. So you have the hot gas rising, it's bright, and you see that the center of the granules are bright. It expands and cools and sinks back down into the dark intergranular lanes. So these granules have lifetimes of about 5 minutes. So the whole outer atmosphere of the sun is very, very turbulent. So these convective flows, these turbulent convective flows, generate pressure waves. So waves are anything that is displaced from its usual state and it returns on a regular basis. Pressure waves are sound waves, acoustic waves, or seismic waves. I will sort of use those interchangeably. But my voice is changing the pressure in the air, and that's traveling through the air to your ears, and you're picking that up and interpreting that as something meaningful, I hope. But this convective turbulence does the same thing in the sun. The waves are generated in the convection. They propagate through the interior of the sun. They reflect off the surface, so they bounce off the surface, and they propagate further. So high wave numbers are sensitive to the surface, and low wave numbers are sensitive deeper down. So it's kind of like a bell ringing. They're trapped inside, except we can hear the bell because it gets out, and this is all trapped inside the sun. We'll zoom in a little section of the surface, and we'll treat it as a box. So here's the surface of the sun, and it gets hotter as you get into the center. So why do waves reflect here? Physicists aren't allowed to answer.
Physics, that's a high impedance surface. So the vacuum above, you've got measurement density below, that's a high acoustic impedance.
Yes, so the density changes drastically at the surface there. So as I'm speaking and my pressure wave goes out, it will bounce off the wall and back into the room because the density changes. So there we have reflection at the surface. Why does it turn over? Refraction, yes, that's what we call it. So what I've drawn on here are the wave front. So it's not a line. The line shows the path the wave takes, but of course it has some width to it. So the wave front on this side, it's going to be slightly hotter and it's going to travel slightly faster. And so with that traveling faster and the top traveling slower than that, it turns over. So we have refraction and reflection, and that's what causes them to bounce around in that pattern. Now these waves, when they get to the surface, they're a pressure wave. They push up on the surface. They reflect, but they also push up. And we can observe that. So most of the observations I've shown you, and will continue to show you, are from the Solar Dynamics Observatory. So this is a satellite that sits out and just stares at the sun. It's got 3 instruments on board. I'm showing you observations from AIA, which is the outer atmosphere. And what's important for the interior is the HMI instrument. So this was launched in 2010. It's been observing for quite some time now. So we have a lot of data. HMI takes an image of the sun every 45 seconds. It takes the surface magnetic field, the surface intensity, and the surface Doppler velocity, which I'll talk about in just a moment. We have set up here the Australian Data Centre for SDO. It does not contain all the data. It contains all of the metadata. So we can search it, but the idea is that we can pull and push the data as we need to. But each of these images is 4,000 by 4,000 pixels. So just to give you an idea of the size of that, this is a picture of my desk from 2011 when we first got science grade observations from SDO, just to show that we can only get the bottom corner of the sun in a full resolution screen. So these are the highest resolution, absolute state-of-the-art observations of the sun that we have. So here we're looking at the Doppler velocity of the sun. The dominant signal you see, so the Doppler velocity tells you if something's moving towards you or away from you. The dominant signal you see is that one side is moving towards you and one side is moving away from you. So you've already seen that the sun rotates, so that's the dominant signal that you're seeing. But if I take that out, you can see better on my laptop this kind of granular pattern around the edge. This is the top of the granulation scales, so you can see them better side on. And then if I take that signal out, you're left with this flickering, and that's the waves. So if it's brighter, it's pushing up on the surface, and if it's darker, it's moving away from you. So towards and away. So you can see those waves. I'll zoom in a little more, because it's very exciting. Oh, not fantastic. Here we have two sunspots, but that flickering you see is the waves. So we can use those waves. We know the background structure of the sun fairly well, so looking at changes in these waves tells us about what's happening below the surface. And that's what we call helioseismology. So this is a technique we use to look inside the sun. It's similar to Earth seismology. Traditional Earth seismology, though, has one source. It's an earthquake. The waves propagate out, they push up on the surface, and you can measure that with a seismometer. The entire sun is covered with sunquakes, so we have sources everywhere. One change to the waves we can look at, so I'll just explain to you a little change, one of the changes that we can look at to build up an idea of what's happening below the surface is the travel time. So we've got our box again, here's the surface of the sun, here's the depth. We have a wave come in, it pushes up on the surface, sometime later it pushes up at another point. So we can watch those 2 points, and it will push up here at one time, sometime later we'll see it push up at another point. If the wave passes through a patch that is hotter, what do you think will happen to the wave? It'll speed up, exactly. It'll be hotter, so it'll travel faster, and our travel time will be shorter. So, there's something below. What happens if there's a flow in the same direction as the wave is traveling? Anyone? Elongated? Speed up. If you're swimming in the same direction as the current, you'll travel faster. So you'll get, again, a shorter travel time. How can you tell the difference if it's a hot patch or if it's a flow in the direction of the wave travel time? The wave is traveling. Close. The time, we're talking about time, distance, velocity. So what you could do, for example, is you could look at a wave traveling in the opposite direction because you've got waves, you've got sources everywhere. And if you're traveling against the flow, you travel slower, so your travel time is longer. Exactly. So that's the way we can tell. This is just one simple example of how we can tell whether what we're looking at is a temperature perturbation or a flow beneath the surface. So just to recap, we know that the sun's magnetic field is very important for space weather. We want to understand what's happening inside the sun. We know that that's where the magnetic field is being generated. We have a technique to do that, helioseismology. So what are we looking for? The magnetic field has an 11-year cycle. It's being regenerated. It's not static, it's not dissipating. It keeps being regenerated within the 11-year cycle. And we know that this is happening somewhere in the sun. So we want to understand this, and this is called the solar dynamo. This is a dynamo process, regenerating a magnetic field. So in astrophysics, this is one of the fundamental problems, is trying to understand how a star and the sun generates its magnetic field. To regenerate it, something has to be stretching, twisting, or shearing this magnetic field to get it to regenerate. So that's what we're looking for in the interior of the sun. This is here showing the surface. Here's a sunspot. This is a sketch. This is the convection zone, the radiative zone, and the core. Here you're looking at one of the most famous results from helioseismology, which is this is the shell, this is the surface, and this is the interior rotation. So the average rotation rate of the sun is every 27 days, but it rotates faster at the equator than at the poles. And we know this not just from helioseismology, but we can track the rotation of the sunspots and we can see how fast it rotates at the surface. But in the interior, we found that, well, anything below the radiative zone, the sun rotates like a solid body. It's all rotating at the same rate. But out here, it's rotating differentially. And at the base of the convection zone, you have this rotational shear where one layer is rotating much faster than the layer above it. And this fit very nicely with dynamo theory. So this must be it. This is where the global magnetic field is being generated, in this shear. So the idea was that this is a sketch kind of indicating where we're looking through the surface of the sun. Somewhere below the magnetic field looks like this, and we bet it's in this area here. We have these active regions. Presumably, they are a direct consequence and they are directly connected to this deep magnetic field. They define the solar cycle. They must be rising from the interior magnetic field. So we have our sunspots. This is the only place we can measure the magnetic field directly, is at the surface. This is as close as we can get to that interior magnetic field. And they extend outward into these beautiful loop structures in the outer atmosphere. So what we think is happening is that there is a deep magnetic field. Somehow this rises towards the surface. We get the magnetic field pointing out of the surface, the loop, and the magnetic field pointing into the surface. So this is a zoom in on an active region emerging, so you can just see how that happens. My argument is this is if we can understand how active regions emerge onto the surface, we get an idea of the physics of what's generating them and where they are coming from. So this is where my research is centered, understanding this process. What I found, and this is an entirely other talk, is that convective flows are important. So the convection is important in bringing up this magnetic field. It's not just barging through the convection and coming through all by itself, which is what dynamo theory would predict. That the convection and the flows is bringing up this magnetic field. So maybe it's not so much this picture, but maybe it's something more like this. This is a global simulation of the magnetic field in the convection of a star. But you can see these sort of structures here that may emerge onto the surface as active regions. So this is changing how we think about dynamo theory. So we have these two options. The magnetic field could be here, the dynamo could be generated at the base of the convection zone in this shear layer, or perhaps it has something more to do with the convection. One of the problems we have in making that decision, or constraining that, is that we only have one sun, and we can't do experiments on it. We can't push it and make it rotate faster and see how that changes the magnetic field. We can't open it up and dig below and see what's happening with the magnetic field there. But we do have other stars like the sun that we can look at. So So if we could look at other sun-like stars, and one rotates a little faster, one has a little more magnetic activity, one has a longer magnetic cycle than the other one, we can probe this and try and understand whether it's more convection or more shear on what's driving the dynamos. So in the same way that we have helioseismology, we now have a very active field, maybe in the last 10 years since observations became really feasible on a large scale, we have astroseismology. So it's the same principle, except for the sun, we can see it in 2D. We have spatial resolution, as you saw from those beautiful movies. But for a star, we only have a point of light. So we can only look at the global oscillations. And what I'm excited for, what's coming up, is a European Space Agency mission called Plato. Now, the goal of Plato is to find an exoplanet orbiting a star. So it passes in front of the star, the light dims, and we can measure properties of the planet. These observations are at a very high cadence, so we make an observation every minute or less, and so they're very suited for astroseismology as well, so you learn about the star. The search space is going to be the entire sky, out to about 2,000 light years, and the goal is to find a small rocky planet, something like Earth 2.0. And presumably Earth 2.0 is going to be orbiting the Sun 2.0. So there are many thousands of sun-like stars in the sample that Plato is going to observe. So using that, we'll be able to understand much better what is driving the solar dynamo and the dynamo in sun-like stars. So to finish, if there's nothing else you take from this talk, space weather is driven by the sun's magnetic field. Yes. It's generated in the interior of the sun. We have a tool to look inside, helioseismology. From a science perspective, we would like to understand the solar dynamo. That's the key science question. But of course, this will also help us to enable space weather forecasting. So we can move from sort of the nowcasting to the forecasting. So I'll leave it there, and you can look at these beautiful observations of the sun's magnetic field for as long as you like. Thank you.
Hi, Hannah. Sorry, Roger Smith. So I'm way outside my area. Those convection currents you talked about on the surface, are they independent of one another? And if they're not independent, do you get coupled behaviour? And would the coupled behaviour make them give them a defined limit above which they would become unstable and therefore lead to change?
So they're definitely coupled in the sense that they're occurring all the time, all over the surface. While they are the source of our waves, they also damp the waves. So they are also a damping function. So they are something we have to try and remove. When we do helioseismology, we need to do a lot of averaging to average out that noise and get a clear signal. Your last question.
I guess I'm wondering just if they're next to one another, they're likely to be influencing one another.
Yes, absolutely.
And therefore, they'd show coupled oscillatory behaviour. And so they would change together, and there must be a limit on that, and then they'd implode or something.
So that's to do with the density and the temperature structure, which dictates the size of the granules on the star or sun. And so in this case, they happen to be quite small, I guess, in relation to the size. There's also larger convection cells on the sun. It has 2 preferred scales. It's not clear why.
Thanks very much. Hannah, thanks very much. I particularly enjoyed that because I have a bit of a vested interest. I also am interested in magnetic fields. I'm a geophysicist. My specialty is paleomagnetism, which is the record of the Earth's magnetic field in rocks, which has lots of interesting applications, although we don't get to do the cool stuff you do and make the record it out of terrestrial seismology in the sort of way you're doing with the sun. What really gets me interested, though, is there are some substantial similarities there in that mechanism you talk about for the generation of the sun's field, and some differences. Both the sun and the earth share a inner zone which is fluid, is rotating, has a zone within that which is relatively fixed. The shear involved, a lot of the magnetohydrodynamics is similar. One of the big differences is clearly the Earth's field is dominantly dipolar.
Yep.
It's pretty close to a bar magnet with little flickers of more complex structure. The sun looks like it's just about all complex structure. Does it have a dipolar element as well?
Yes. The global field of the sun is dipolar. I'll ask you, actually, let me go back to this one. This movie shows the full disk of the sun. In this case, the magnetic field is blue and yellow for plus and minus instead of black and white. Don't let that get away. And now what's going to happen is going to unwrap, and I hope you'll be able to see the magnetic field at the poles. So you can see it's slightly yellow at the top, and it's slightly blue at the bottom. So that's that global dipolar field, which is very much like the Earth's. And that, if you look very closely, so here you're watching the movie with time, you'll see it flip. So in each 11-year cycle, this magnetic field is flipping.
It's also, I find that really intriguing. That I know that there's that 22-year element, the flip every second cycle. That's really intriguing to me because I'm very much interested in reversals of the Earth's magnetic field, which are aperiodic. They don't have any particular cyclicity at all. They go from, we get intervals as long as 64 million years. The Kiama interval, which was discovered here in New South Wales, recognised in Kiama and locally here in the Hunter Valley, which is the longest interval we know of constant polarity, to intervals as short as a few thousand years. So the sun is chaotic in one sense with all that incredible detail, but it's got a much more steady pulse than the Earth, which I find really intriguing.
Yes, and for the non-physicists, I think there's a distinction between planets, gas planets and stars, the dynamo in gas planets and stars, and of rocky planets. There's a distinction between the physics there. So for the Earth, it's probably generated by a slightly different physics than what's in the sun.
Yeah, well, it doesn't have that complication of that surface convection, but the inner shell element does. That's got a lot of similarities. Your rotating system being torn out by shear, it's very similar.
Okay. Thank you.
George. Hello, my name's Warwick Giblin. I was fascinated with your real-world examples of where the sun has influenced events on Earth. Particularly the one about the Quebec power failure in 1989. We're about to build 10,000 new kilometres of transmission line in Australia. I mean, how common is it that some variation, as a consequence of a CME from the sun is influencing our electricity distribution network system here on little old Earth?
But we'd never know until it happens. So at the poles, it's much more likely. At lower latitudes, it's not clear, but there hasn't been a lot of research on it, is the other thing. And so we have also these long gas and oil pipelines, so these also conduct electricity. And maybe it's not something that puts the power out immediately, but it degrades the material faster than what's predicted. So it's I've presented here the very drastic examples of what's happened, but there can also be much more subtle examples.
And a supplementary question, Hannah, to that is, like those who design our electricity distribution system, for example, is there some provisions, contingencies built into their designs to accommodate some CMEs?
Yes, so particularly after that Quebec incident, when they reconfigured it, and I'm not going to try and tell you what it is, Wikipedia will tell you exactly what they did, but they did realise that and built in mitigation strategies, and that has been adopted at least at high latitude power stations.
I see. Fascinating. Thank you.
So you said how the there are cycles, 11-year cycles with the sun's magnetic field. Do we know exactly why there are those cycles and how come 11 years? Like what causes that?
Great question. So in a dynamo mechanism, it's the flows that are driving the magnetic field and doing something to it, stretching, twisting, whatever. So it's the slowest flow in that system that will dictate the period. In the sun, there's a flow that travels very slowly at the surface from the equator up towards the pole, and then somewhere in the interior it has to return. And that return flow is about 2 meters per second. We can put upper limits on it. We can't see it directly because it's so low. And that gives you 11 years. It takes you 11 years at 2 meters per second to return down back to the equator and again. So we think that is the flow that's dictating our 11 years.
I'll ask a very stupid question, or very basic rather. So, it seems like a lot of your research is the overarching application will be to be able to predict some of these events, ahead of time. How far ahead do you think that they could be predicted, and what do you think is going to be the most obvious or easiest way to do that?
So the part we sort of really care about on the space weather forecasting scales is perhaps not the 11-year cycle for space weather forecasting. But if you can predict when an active region is going to emerge, and perhaps whether you could say at least whether it's going to be complex and strong or weak, that would give you up to a week's forecasting. Because if it emerges here, and then it flares at this time. Exactly. So it needs to, one, emerge, whether it's large or small, maybe you can say something about it. Then you have to be able to say whether it's going to flare or not. Then there's the question of whether there will be a CME. In which direction is it? Is it directed towards Earth, or will it be deflected by something? Then what happens between the sun and the Earth is a relatively big unknown. As I said, those observations are quite special. We don't have many of them. We can't really see what's happening. We don't have a lot of statistics until it reaches our satellites, which are near Earth, and gives us an hour's notice. So there's a lot of kind of parts to that need to be forecast. Up to a week, optimistically.
Cool, thank you.
So I presume nobody's taking into account the 11-year cycle when they're launching their rockets and things like that?
Yes, absolutely. So when planning space missions, especially with the upcoming moon to Mars, but also with satellites that are sent out into the solar system, that needs to be taken into account for degradation, how much radiation they're going to receive. If there is even closer in for the satellites, they can be pointed away from an incoming coronal mass ejection from the radiation and shielded. So it's absolutely taken into account, yeah. So that 11-year cycle, when should we launch it? How much will it degrade? Should we wait until it's, solar minimum? That might be a safer time to send it. Yep.
I've just got another anecdote to add to your list of samples. In 1972, there was a large magnetic storm in August. I happened to be working at NOAA in Boulder, Colorado at that stage, and the director of the lab said, I've just had a visit from a lot of high-up suits from Washington in the Navy and so on. And I asked him what that is about. He said, I can't say anything, but watch this space. And 20 years later, the data was released, and we found out that during the Vietnam War, August 72, there was a large magnetic storm. It wasn't the magnitude of the field that counted, but it was the rate at which it changed. It changed by about 1,000% in a matter of a second or two. And what happened, the American Navy had put a whole series of magnetic mines in Haiphong Bay in North Vietnam. And the Navy, US Navy noticed, and people going by noticed the odd one of these started to explode over this period of 4 days while they had a magnetic storm. And it turned out it was the mechanism got triggered by the change in the Earth's magnetic field.
Right, so the
And
mines are...
at that stage, they came to the lab in Colorado to figure out what their maximum level should be so they didn't do this again. So it's interesting how this, and the paper was written only about 4 years ago on this when it's finally known. So there's a lot of anecdotes of what goes on, a lot of things that happen.
Yeah, I think that's a really nice example. It's also at a low latitude, and Brian clearly got the early news 20 years ago, but they declassified the documents only at the end of the 2010s.
That's right. I had a friend in the Air Force over there.
But the mines are designed, they detect changes in the magnetic field, and when an ion ship passes over the top, they'll explode. But the magnetic field was clearly changing so much, even at the bottom of the ocean, that it set them off.
Yeah.
So that's...
One last comment. I'm a little worried about the current situation about our research in space physics and space weather in general, here in Australia and also in the USA, with the mass sackings that are going on within NOAA and other scientific agencies. I think we've got to watch the space quite carefully and hope we're not affected too dramatically, because as Hannah showed you, we're all used data from all of these satellites that either belong to the European Union or belong mainly to the USA and some Japan, but that's about it.
Ask a technical question. I've got it spinning, and there's shear. I eventually think that shear is going to, it's going to bring the whole thing to move together. Why would the friction will want it to move? Why is it not move?
Wonderful question. It's also, the question also is, why is the equator rotating faster than the poles when it should be the other way around? So there's a question of angular momentum distribution, and so the magnetic field was a great way to decouple that radiative zone in the interior that's rotating a solid body to the outer convection zone. So that theory that the magnetic field, the global magnetic field is seated there, is also very nice for the angular momentum problem, that it's
moving driven by these convection cells and
the convection, the meridional flow, but simulations, we don't know enough about the physics to model that yet. Yes, these are open questions. Thank you very much for coming and your attention. It was very lovely.